any questions, and we can figure out some workshop later. Thank you so much.
Okay, so I
Bye.
start recording. And now it's time to get hands on with artificial intelligence. And our next speaker, Tarun R. Jain, will guide us throughout building a local agentic RAG system using Gemma, 3M, and Qdrant, all running locally, no cloud required. You will see how to process data privately, trace and monitor your workflow using Comet OPIK, and experience the power of fully local AI in action. So please welcome Tarun for this practical and insightful session. Feel free to, so I will stop sharing. Feel free to start sharing. Dear attendants, feel free to share your questions. And one more time, biggest thanks for your time. And I'm sure that you prepared amazing workshop. So welcome, Google developer expert, blogger
Thank you.
now.
Thank you for the introduction. I hope I'm clearly audible, right?
Yes, right.
All right. So there is just a power cut, so I just wanted to be sure that my voice, the light might probably come back again, but probably we can get started. So hopefully there is no internet facilities issues. So today, what we'll do is today we'll try to understand how Agentic RAG application works, how we can use routing systems when it comes to using multiple tools. So what this is about, how this works. So this is what we'll be talking about in this entire session. So before we can begin, here is a quick introduction about myself. I work as a founding engineer. It's a self startup at Luxembourgish company. We basically work in the fintech domain. And apart from that, I also have a small YouTube channel called AI with Tarun, where I typically share everything around agents, RAG, function calling, and everything around LLMs. And in my free time, I also travel around. I give talks at multiple conferences. I'm an active PyCon speaker, and I've given many talks at Asia Pacific region, and it was part of the Google developer expert ecosystem. And apart from that, I love contributing to open source. So I've been part of Google Summer of Code for 2 consecutive years. In 2024, I was part of Red Lab, and in 2023, I was part of CA Microscope. All right. So before we can begin, here is a basic understanding we need to understand. When you ask any question to an agentic application, the intent matters the most, right? When it comes to intent, it can be the keywords that you use within your prompt, and where are you supposed to route the specific query. It is very important. So when it comes to routing the query, you have multiple tools. So this is what we'll try to understand in terms of how agent application works, right? So here is a simple task. So the task here is, what's the forecast for tomorrow? Should you take the umbrella or not, right? So if you notice this particular task, you have two questions. So the question one is to understand what is the forecast for tomorrow, where you are getting the context, right? So the question one will get the context, and the second question, should I take the umbrella, will get that context and do the reasoning, right? So this is the goal. Now given the task, you have multiple tools, right? You have YouTube, you have Google, you have GitHub, you have Yahoo Finance. So where do you think agent will route this particular task to which tool? So can anyone just write in the chat which tool do you think is most relevant, so that we can have interactive session? I hope I'm clearly audible. Correct. So we did get the response again. So here, basically, when you have any task related to weather API, Google is the most relevant tool that can be used. So you're taking that action. So if you notice the entire steps that we have taken, you have task, and after task, you have multiple tools where you can route to. And once you route to the specific tool, that is the action step that you're taking. And once you have the action step, you're getting the context for first question, and that context is now given to your LLM, which will generate the final response, right? So this is the high level understanding of how agentic application works. And here is a very simple differentiator that everyone needs to understand. Consider time is 7:30, Now, if you ask a prompt saying good morning to a large language model, you will get a response like, good morning, how can I assist you today? Even though the time is 7:30, it doesn't matter what the time is. You're getting a very generic response. But now if you ask the same question to an agent, if you notice you're getting good evening, it seems it's still nighttime. But if you're greeting me with good morning, maybe you're preparing for a fresh start. So what are the two things that agent does differently? First thing is the tool calling, right? Agent has flexibility for the given user task. It will understand which tool is relevant and it will gather the information real time. So first one is the real time information using function calling, and the second capability is the decision making, right? So once you get the context, how are you generating this particular response? So decision making is very important. So now you might be curious, right? How do this decision making capability works? So what are the different prompt techniques that one can utilize? This is where you have a concept called react. React stands for reasoning and action. So let me explain this in a very simple terms. So as I said, we'll be utilizing this paper called React, which was again developed by Google DeepMind team. So here I have a very simple prompt. The prompt is pure vegetarian restaurants I need to find in Prague. So this is my user task, right? So once you ask this particular prompt to an agent, first what it will do is it will try to think what it is supposed to generate the response. So when you do the thought process, you're using one LLM call. So if you see, you're using thought, then you have generation reasoning. And if you look at the thought process, what it is trying to do is, okay, I need to look for pure veg Indian food in Prague, right? And now once you have the thought, the next thing is action, right? So when action is coming into the picture, you will have multiple tools available with you. So here you have web search, you have calculator, you have code execution. So among these three tools, agent will think web search is the most relevant. So now it will pick that particular action. So you have thought, you have action, then you have observation. In observation, you're generating the final response. Now it doesn't stop there. Agent will try to think whether this is the right or reliable response to give to the user or not. So here you will have multiple user inputs that will be given in order to make this decision. If the goals are met, you have your final response. If the goals are not met, typically in a React, it's a loop. You it in a maximum iteration. So you have iteration, iteration 2, iteration 3, iteration 4. Once it reaches the maximum iteration, you're stopping. If not, you will again go back to the thought. So it's like thought, action, observation, thought, action, observation. If you have the final response, it will generate the final response to the user. So this is how decision happens in most of the open source frameworks that you're using, right? Whether it is CrewAI, whether it is LangGraph, you have pre-built agents called Create React Agent. So this is where you have decision making capability, which is interacting with tools and getting the real-time information. All right. So here is where we discussed what is agents. And now comes the second topic, which is RAG, right? So the goal is to build agentic RAG. Agents will get the information real time. It will do the reasoning. But what about your own data, right? If you want to build a very solid system for your own data, and if you want to feed the relevant chunks to the large language model, this is where we have a concept called retrieval augmented generation. So quickly, I just wanted to know how many of you have already heard of this concept before? Is there anyone who already knows what is RAG? We can just see a quick answer. Okay, we have Sarthak who has already heard this concept. All right, all right. So I see few hands. Good. So in simple terms, if you want to have a large language model to answer the question that is relevant to your data, this is why you use RAG. So in simple understanding, there are two components. The first component is your document processing, and the second component is the answer generation. So for document processing, you have the external data. You're giving that external data into multiple chunks. Why do we need this chunking process? Most of the large language model has limited context window. So it's better to chunk the data and then give it to the vector database, right? So chunking is one. And second thing is, most of the time what happens is instead of giving the entire data, you can better give the relevant data, right? So you have a testing technique called needle in the haystack. So your needle is nothing but your query, haystack is nothing but the context. So once you reach the larger limit of the context, the information starts getting to lose, right? So this is where having better chunks is very important. And once you have the chunk data, you need to save chunk in your vector database where you'll be using embedding model, right? So this is where you'll be using dense embeddings. Dense embeddings is mainly used for vector search, right? So you'll save both of this. If you see the arrow mark, see, you have your chunk data, you have your embedding, you're saving it in a vector DB. So once your data is inside the vector DB, here comes the second part, which is your real-time answer generation. So user will ask a question that will be converted into embedding. You will look into the vector database, get the relevant chunk using your search technique. It can be maximum marginal relevance, it can be similarity search. Based on that, you are getting the chunks that will be given to the LLM. So now if you look at this LLM, it has two inputs. One is the chunk, one more is the query, and then you have your final response. So this is how RAG works. But what we will do is we will use a technique called hybrid search, which was also referred in a blog article that Uber had released. So if you look at this article, Uber released an article that says how they built their enhanced agentic RAG. What if chatbots could deliver near human precision? So if we look at their architecture diagram, this is how it looks like. So if you look at the bottom, this is what you call as offline document processing, where you have your data, you are adding additional metadata, and once you have your additional metadata, you have your embedding model, you're saving it in a vector DB. The interesting part, what you are supposed to say is, when it comes to your answer generation, you have your vector search and as well as keyword search. So this is where you have your hybrid search approach, where you're utilizing your retrieval process. To those who are not aware of what these dense vectors or sparse vectors are, let's understand this in a simple terms, right? So you have dense vectors, you have sparse vectors. Dense vectors is basically used for vector search. Sparse vectors are basically used for keyword search. So let's take an example that you have a query called neural network. So if you check this with keyword search will only extract those documents which has exact same keyword, which is neural network. But when it comes to vector search, it will look for schematics, right? What is the most relevant keywords or what are the matches? So you are trying to find the distance measurement, the pairwise comparison. So here, when you search for neural network, you will also get AI, you will also get deep learning, you will also get machine learning. So what we will try to do is we'll combine both of them in our application, which I'll show shortly. So this is what we'll try to build. And along with this, since we need our entire application to be agentic RAG, we also need to have a tool routing system. So what this routing system will do is, if you ask any question which is relevant to the vector database, it will match your retrieval process. If your question is not within the data, it will use Google search. So this is what we need to do. If your question is within the data, use vector database. If it is not within your knowledge base, you will use web search, which is your Google search, and then you will have your final output. So this is a kind of routing system that we will try to develop. And again, so now that we know the concept, before we proceed with the demo, here are some quick questions that we need to answer. So why are we supposed to run everything locally? I work in a fintech domain. When it comes to fintech domain, most of the startup or enterprises, they're not okay in using closed source large language models like Gemini, OpenAI, or Claude, right? Because they are closed source. So this is where they need full control. They need their privacy because most of the data is confidential. And there is also a segment where you have multiple data, you want to fine tune your own model, right? So this is where having open weight models are very important. And this is where we have Gemma 3, right? And Anna and Arpita have shared lots of details about Gemma 3. And I had the similar thoughts. When it comes to Gemma 3, there are three areas where it is pretty excellent compared to other open weights model. One is the multilingual. As Anna already mentioned, most of the times you have translation issues, right? You need the native tokens, right? If you convert anything from English to German, you need that native touch. So this is where, when it comes to multilingual support, Gemma models and as well as Google family models are pretty good enough for multilingual, because they had an internal project called Bashini, where they collected multiple Indic languages and trained their particular model. So this was one project which was related to Indic languages, but similar might have been applied for European languages. And then comes multimodal support. If you need anything related to audio, video, images, it understands pretty well. It uses something called as SIG-LIP, which is a encoding model, which is used within your Gemma models. And one more interesting thing about Gemma is there is a concept called KV cache, right? So the KV cache for larger context window, there is a sharing concept, KV cache sharing, which is introduced in Gemma 3, which makes the long context processing very fast. So this is where we'll be using Gemma 3, and one of such that model is Gemma 3N that we will be using in our demo. And apart from that, you also have 270 million parameter model and 1 billion if you are looking for anything on the edge devices. And then you have 4 billion models, then you have 12 billion and 27 billion parameters. All right. So now what is the issue that we are trying to tackle? The major issue that we have in this entire code demo is Gemma 3 doesn't support function calling, right? So if you look at the entire Gemma application, most of the open weights model natively support function calling. But if you want to use React, you need the base model to support function calling natively. So which is not there as of now in the Gemma models. So what we will do is we have performed prompt engineering using delimiters, which are hard coded, which will mainly be used for routing our function callings. And once you use that function calling, we will have the interpreter, which will get the final output. I'll explain this when we have the code demo. But how did we come up with this approach? There is one Googler who is named as Phil. He released one article called How Google Gemma 3 Can Be Used for Function Calling. And apart from that, if you see, there was one open source contribution that was made, and that contributed me. So if you just open Gemma cookbooks, you will find only one example that was related to function calling for Gemma 3. So this is where I added that support, which was inspired by this article, where you can use prompts with delimiters. So delimiters is nothing but you have 3 tokens that you can utilize. And then once you ask the prompt to the LLM, it will generate those delimiters. I'll show this in the code demo. But this is the brief understanding, the problem statement that we are trying to solve, that function calling is not natively supported. If you want to build local agentic RAG, we need to have what you call function calling support, which is done via prompt engineering. All right, so this is a demo time. We have spoke a lot. It's time to look at some code and try to understand how things works. And before we jump to the code, here are some key takeaways that we will try to learn in the code demo. First, we will try to understand how we can use Ollama within the Colab system so that you can utilize free T4 GPUs that you're getting. And apart from that, as I already mentioned, Gemma 3 doesn't natively support function calling, but we do have separate support that can be used to utilize the decision-making capability of Gemma 3N to route the function calls. And then we'll also be implementing hybrid search, which will improvise your retrieval process of your pipeline, which is mainly used for dense vectors and as well as sparse vectors. And then we'll also see how you can do tool routing. All right. So if anyone is keen to learn more of this, and if you want to learn about MCPs and anything related to EIML, you can just check out this particular channel called AI with Tarun. It's a selfless promotion. All right. So this is the Colab notebook. Let me also copy this URL in the chat. Meanwhile, before we jump to the demo, does anyone has any questions? Just let me know if you are able to see the Colab notebook. Anna, can you confirm if the QR code is correct?
But you share. I saw that you shared link, but not in our main chat. Maybe you can repeat and in main chat.
Okay. So it's just bit.ly/local-agentic-rag. So once you open this URL, you'll get the Colab notebook. So I did click on chat and I pasted it here. So is this visible?
One second. No. Now, yes, now it's visible.
Okay, perfect. All right. So this is the Colab notebook. And if you see, I've divided the entire Colab notebook into 4 different parts. The first part will try to understand how to load Olama models on Colab, and I'll briefly touch base on every single line of code because sometimes running Olama takes time. So what we'll do is I'll touch base on that, and you also need T4 GPUs. So most of the time you'll not get T4 GPU support because there are too many people they're utilizing. So this is where someone can upgrade into Colab Pro and get the GPUs. But we'll understand the process line by line so that if anyone has any doubt, we can address those issues. And then in the part two, we'll try to understand if you have any data, how do you process the data into your vector database, and what are the different techniques that you can utilize to improve the process. We'll try to understand that in regards with how Uber has done it, right? So as I said, Uber has their enhanced agentic RAG, agentic RAG Uber. So this is the article, and this is the architecture diagram that we'll be tackling. And when we tackle this architecture diagram, they have also used multiple different loaders, right? Why did they pick that loader? What was the justification behind it? We'll try to understand that in the second part. And in the third part, what we'll try to do is your data is saved inside vector database. Now, how do you perform tool routing and how do you build your LangGraph nodes? So this is what we'll try to understand in the part 3. And then for part 4, because most of you want to have something UI, because if you build something, you will probably need it to showcase it to someone, right? So this is where you can also have a Gradio UI that can be reshared with others who can test your application. So this is how we'll divide our entire code structure to look like: part 1, part 2, part 3, and part 4. So before we can start with the parts, it's good to start with the installation step. So for installation step, first we have LangGraph. Why are we using LangGraph? It's because we need the LLM component, vector databases. LangGraph is mainly the wrapper around all of this. And one better part about LangGraph is the state management. It's state management and graphical graph-based node representation. So now what is this node? This node is nothing but your Python logic. So now let's imagine you ask a prompt, you're using a tool. This tool will generate a specific parameter. That parameter will go to the execution tool, which will generate the response. That response needs to be given to the LLM. So if you see here, you have multiple nodes from which you have to get that logic. So if you want to manage all these things at a single particular time, this is where LangGraph works pretty well. And then you have LangChain community. Now, why do we need LangChain community? You have your own data, right? Data can be in form of PDF, CSV, Excel, YouTube. It can be in any format. If you need those loader support, which will extract your data, external data into raw text data. So this is where we will be using LangChain community, which will mainly be used for loaders, right? To extract your raw data, to extract the raw data. Now comes the next part. Here, if you see, you have LangChain Qdrant. This is your vector database that we'll be utilizing. And there are 3 ways you can run vector databases. How you can save your data inside vector database. The first approach is cloud. You can utilize the cloud providers of vector database. The second approach is Docker. You can run your vector database instance locally and then save your data over there. And third approach is in-memory. So in-memory is nothing but you will create a path within your project directory where your data will be saved. So in our entire code approach, we'll be utilizing the third one, which is in-memory. So you have a project, your data is saved only within that project. If you try to access that outside your project, you won't be able to do it. So if you want to access your data outside that folder, you can use Docker for local instance. All right, the power is back and the light is on. Cool. So now coming to the next part, you have LangChain Olama. This is mainly used for your LLM component, which will generate the response. And then you have PyPDFM. Now, this is a tricky part. Why am I using PyPDFM? So if you notice this article, you have your data. What Uber is trying to do is you're building a Slack chatbot for which you have some policy documents. So this policy document is PDF. And what Uber tried to do is they're loading this data using Google Drive. So if you see, GDocs is nothing but Google Drive. So now what is happening is all your PDF content is extracted in a document format, which is a API, and then you are extracting that in a markdown. So when they did this, they tested with multiple state loaders. So if you see, they experimented with different PDF loaders. You have simple directory reader, you have PyPDF, and then you have PDF plumber, PyPDF, PyMU and then you have Llama index parsers. So after trying all this, they found out Google Docs worked well, right? And apart from that, in my video, so if you just search for enhanced agentic RAG Uber, you will see two videos over here. So if you see, both are by me, AI with Tarun, AI with Tarun. So I did had one presentation. Let me show that. So for document processing, as you can see, there is a paper called comparative analysis. In the comparative analysis, they have tested data set against financial, gender, law, scientific, manual, and patent, and they found out PyPDF works much better compared to other PDF loaders such as unstructured, PyPDF, Plumber, and as well as MUPDF. So this is the reason why I am using PyPDFM compared to other PDF loaders. And the paper is here. So if I just open this paper, it's just called a comparative study of PDF parsing tools across diverse document categories. So this is the paper that I referred to use PyPDFM. And then since I said, if the question is from the knowledge base, we'll use the knowledge base tool, which is our vector database. If it is not from the knowledge base, and if it is a generic question, we'll use search. So for search, we'll be using DuckDuckGo. And last, for monitoring, we'll be using OPIK for monitoring and tracing. And if in case Olama is pretty, it's taking too much of time, just for this demo purpose, I didn't wanted to intend to use this, but if in case we are against the time and we have lesser time, what we will do is, instead of using Olama, we'll be using LangChain Google Generative AI. So Anna has already mentioned about AI Studio. So if you look at aistudio.google.com, you have multiple models that are already hosted. So these models are both your Gemini family and as well as Nano family. So if you want to use any Gemma models as well, you can use the Gemma models from there. So we'll be using Gemma 327B IT. So one model we'll be using from here, and the main model we are using it from LangChain Olama, which is Gemma 3N. So if you just open Olama category, so you have a library. Inside this library, you have multiple models. You can just click on Gemma 3. Here you will find there has to be Gemma 3N. Gemma 3N. So this is the model that we'll be utilizing. If you see Gemma 3N, you have E4B. So you can just copy this particular model. Now come back to Colab. And the first step, what you're supposed to do is, which is the inference Olama on Colab, there are two commands that you're supposed to run. So basically, Olama has a serve command, which is running on a local host, which is 127.0.0.1, and the port number is 11,434. So now what the issue is, when you run the local host, it is running on your instance. But if you're using Colab, you need this local host to run in the Colab instance. So this is where we'll be using this command, which is no hub, which will save a particular file called Olama log. So once you have this particular file saved inside your system, you can utilize your Olama, right? So I'll not be running this because this takes time. And once you do this, you have model name. Model name is nothing but Gemma 3N E4B. And once you define this model name, which was mentioned here, you can directly import Olama, and you can use a function called Olama pull and that particular model name. So what you are supposed to do is, you need to see your progress response, which is status success. So in my opinion, this step will take around 3 to 4 minutes to load the model. So this is just one-time approach. Once the model is loaded, you can inference it any point of time within the same instance. Because if you see, the size is 7.5 GB, which takes some time to download depending on the internet speed. All right. So now once this is done, we'll also be testing the model. So if you look at the testing of the model, again, you have already imported Olama. You'll be using olama.chat, which is the completion command. And then you're defining your model, which is the same. And then what you're trying to do is, you are asking a question called, what is so special about Germany, and you have the response is inside message, then you have content, and if you see, you have this detailed response which was generated by Gemma 3N. So this is the part one, where we wanted to understand how you can use Olama on Colab utilizing T4 GPU. So if anyone is not sure of how to use T4 GPU, you can click on runtime, then you have change runtime type. Here you have to select T4 GPU. All right, so this was the part one. Let me just check if anyone has any questions before we can proceed to part two.
Not so far.
All right, no worries. So this is the part one. As I said, we are just running these two command, and whatever model you need to pull it, just define that model name, and you have to see the success message. All right. So next part, what we are trying to do is we'll be utilizing our document processing. So for this, I'll make sure I have my slides ready as well. So what are we supposed to do in document processing? First, you have your external data. In our case, it is PDF, and then you have to do chunking. So when we are using PyPDFM, it will already chunk our data. And once you have the chunk data, you also need to have your embedding model. So for embedding model, we are utilizing fast embed embeddings, which has both dense embeddings and sparse embeddings. And then once you have both of this, we'll be saving that inside a vector DB. And the approach that we need to do is the hybrid search approach, which I'll talk about in a minute. So if you see, you have your data extraction and chunking. I'm using the file system, blob loader, then generic loader, and PyPDF loader. So why these two things are added here? So these two details are added because my data is inside a folder. If you have a direct single file, let's suppose if you have a single file PDF, you don't have to define these two lines. You don't have to define these two. You can directly define your PyPDF parser and define your path. That should work. So since my data is inside a folder, what I'll do is I will define both of these two, and all the PDF that is inside that folder, I will parse it. So these are our loaders. And then you have your embedding, which is fast embed embeddings. So from here, we'll utilize both sparse and as well as dense for hybrid search. All right. And then we have our LangChain Qdrant, which is our vector database from which we need to utilize fast embed sparse. Then you have Qdrant vector store, and retrieval mode is nothing but hybrid. So retrieval mode is just a keyword that you have to define, which is hybrid. And here you also have client. So what is client? First, you need to create a space where you have to define what approach you need to take. So here, if you notice, I wrote 3 steps, right? First, you have cloud. Second, you have Docker. Third, you have memory. So you have to define your client, and you have to define which among these 3 are you supposed to pick. If you're using cloud, you need API key, you need URL. If you're using Docker, you need the local path URL. And if you're using in-memory, you just need a path where you have to save it, right? So this is defined in what do you call Qdrant client, right? So these are the import statements. Let's proceed with the data loading. Here I will try to run the code. So if you see, you have loader, you have generic loader. Inside this, you have the blob storage, which is your file system. Now what you need to do is you have to ensure when you're running this particular code, you need to have a data folder. Inside the data folder, you need to have any PDF of your choice. So here I have one PDF, right? And you can have multiple PDFs. You can have 5 PDFs. You can have 10 PDFs. So once you have your PDF, what you're supposed to do is just run this loader, and then docs.loader.load. This is the function that will load the data. And as you can see, there are total 6 chunks. So if you use docs 0 page content, you will get the raw text. And now if you run metadata, you will have the producer of that particular PDF, then when it was created, then you have title, author. What matters to us is the source, total pages, and page. These 3 are very important metadata. Now, what is the purpose of metadata, right? Let's try to understand this. Let's suppose you have 10 PDFs, right? And if you are asking any question, now if you want to tell the user the citation from which PDF the question was responded, you need to have the total page number, and you need to also have source. So this way you can tell, hey, this is the question, this is the answer, and it was generated from this particular page. So in order to rectify the PDF and as well as the page, this is where you need the metadata. So now proceeding next, you have initialize your embeddings. So as I said, we have two concepts. One is dense, one more is sparse. For dense, we'll be utilizing the basic embedding models. So for embedding models for open source, you have Nomic, you have Gina models, and you also have something related to GTE, and you have Qwen models. So Gemma don't have their embedding models released publicly, but you also have Gemini embedding models, which you can utilize. And once this is done, what you're supposed to do is you have to define your sparse embeddings that is used for keyword search. So for keyword search, you have search algorithms, which is BM25, and BM25 stands for best match 25, and then you have TF-IDF, and apart from that you also have something called as BM42. So these are some of the search techniques, and in the recent days you also have something called as sparse neural retriever. It's sparse neural retriever, which uses an algorithm called Minicoil. So these are algorithms which are mainly used for your keyword search. So you have your embedding model, you have your sparse embedding model. Now what it will try to do is it will load that model locally, right? So if you see the starting till here, fetching 5 files. So this 5 files is for your Gina embeddings. So now if you notice this part, Onyx. Now why are we using Onyx and why are we using fast embed embeddings? So instead of fast embed embeddings, you can also utilize Hugging Face embeddings, right? So once you define your Hugging Face embeddings, you are using sentence transformers. So here what is happening is it takes some time to load this model, and this is loading in safe tensors. If you want the safe tensors to run very quickly, this is where we use fast embed, which will run in Onyx runtime. And second thing, what it does is it provides data parallelism, which is supported for very limited models. So you can just search for fast embed supported models, the list of Nomic, Gina, which are open embeddings, right? And then once you have this, what we are supposed to do is we need to start with your indexing process. So indexing is nothing but you create your vector database collection, you save your data inside that collection, that is indexing. So your entire indexing takes only one, it should be done only once. So if you have 5 PDF, if you save that in vector database, that is just once. If your data is getting changed, you will index it again. So indexing needs to be done only once for the given data. And every single time that you do it, you need to have a unique collection name. So now if you see, you have unique collection name that says Agentic RAG, and now you have client equals to Qdrant client, and you're defining a path. So now if I just do ls list temp, then if I do db, you should see collection and you have meta.json. So now if you enter inside collection, you should see Agentic RAG. So you see Agentic RAG. Now if you enter Agentic RAG, you will see a SQLite folder. So all your embeddings will be saved inside storage SQLite. So this will be seen only once you run this particular line. So what you need to do is this line was supposed to be run after you index your data. All right. So let's proceed next. Now, once you define your client, you're defining a space where you need to provide certain configuration. So this configuration is nothing but your vector search, which is your dense, and I have to define my size and the distance measurement. So the size of the embedding model are 768. So here I have one question. How many of you are aware of a concept called dense vectors and sparse vectors, so that I can give some understanding? So dense vectors are basically, you will have 0 0.3, 0 0.4, 0 0.5, then minus 0.9. You will have some numerical digit. So this is fixed. So whatever you have here is a fixed embeddings, right? So here the fixed embedding size is 768. Just like that, you have some embedding models from Gemini, which will have 5, 1, 2, or it can also be 3, 6. So it should be 3, Let me check it out. So supported models, fast embed. So you have this URL, and if you scroll below, it's 384. So if I come back, so either it will be 1512, or it will be 384, or it will be 768, or you will find it as 512, or you will find it as 1024. So these are fixed embeddings. So when it comes to sparse vectors, how are you trying to calculate is, let's suppose you have some documents, document 1, document 2, and here you have sentence called the cat was dead, and here you have document saying that the cat was active. So now what you will try to do is, you have a query. So this query is nothing but is cat alive, right? So now what you're trying to do is, in sparse vectors, you will create a index graph, right? So you have something called as inverted index. So in this inverted index, first what you will try to do is let me show the Excel sheet. So here you have 4 documents. Document 1, Ninja Adventure Fighting Power Friendship. Then you have document 2, Fighting Power Train Super Saiyan. Then you have document 3, just like that you have 4 documents. So what happens in index is, you will add all the documents here, and all the words that you have will be on your columns, and then you will just add this 1, 1, 1. If it is not there, you will make it 0. So basically what you're trying to do in sparse vector is, you're trying to calculate the pair of your occurrence. Pair of the occurrence, right? So either in sparse vector it will be your index, or it will be 0, right? So if you see 0 most of the time, that is where you're using sparse vectors, that says this particular keyword is not there in the given document, and it is marked as 0. So most of the vectors that you see in sparse vectors will be 0. Either it is 0 or non-zero. This is the basics, right? So you have to configure that. So for sparse, you have to configure your index. As I said, it is inverted index. So models dot sparse index params, and I have to load it in the disk, and I don't have to load it in the RAM. And then you are defining your modifier, which is IDF. IDF is nothing but your inverse document frequency, which is mainly used for calculating the frequency of occurrence. So once you configure this, it should show true. And now what you're trying to do is, you will index your data. So when you do index your data, you have to define your client, which is the space. Then you're defining the collection, which is unique. After every data changes, you have to change your collection name as well, like version 1, version 2, version 3. Then you have your dense vectors, sparse vectors, and retrieval mode is the hybrid, because we need the hybrid search. Then you have to define your vector name and sparse vector name, which is this one, dense and sparse. So here if you define dense 1 and sparse 1, here it should be dense 1 and sparse 1. So this is what you have to do. And once this is done, we just have to save our data. So when you save your data, you also need to generate unique IDs. So for generating unique IDs, you have UUID. And then you just run this function called db add documents, which will add your data inside the vector database. So till here, if you do, your vector database is saved inside a SQLite folder within the in-memory location. I hope we are following till here, and we have some limited time. So probably I'll proceed. So once your data is saved, here is where we are bringing the user query. You will ask the question that is relevant to the document, and then we use a search technique called maximum marginal relevancy, or it's called as MMR. So in simple terms, we need both relevance as well as diversity, and this is the reason why we are using MMR. If you don't want to use MMR, there is also something called as similarity search. So if you see, you have similarity search, you can use this one as well. And then you are generating the relevant documents. So this relevant documents is nothing but for the given user query, which one is the relevant. So I'll just run this, and I print the length of relevant docs. It should be 3 or 4. So as you can see, 4 relevant chunks was retrieved. So it is this part. So for the given user query, you're checking into embeddings, then you look into vector database, and you're retrieving chunks. So far, we are at the third step. Now what we are supposed to do is, we are proceed to the LLM part. So when it comes to LLM, we are replacing this LLM with Agentic RAG, which needs routing, which needs function calling, right? So now once this is done, we'll proceed with the part 3. So part 3, basically how it works is you ask a question, then you have Gemini. Here the diagram is Gemini, but it can be any LLM. So what will happen is once you ask a prompt, it will decide what tool to pick. So you have 5 tools, right? Among these 5 tools, you have knowledge base, you have search, you have YouTube, calendar, or any other thing. It will decide what tool to pick. So once it decides the tool, it will also decide what are the function name and arguments within that particular function. And then what it will try to do is it will run an interpreter. So it will try to call that function, get the output from that function, and that output is then given to the LLM. So this LLM will then generate the final response. So how many LLM call is done? Total 2. First LLM call is to generate the function call decision with parameters, and second one is to generate the final response. So I'll show you the output of both of this. All right. So now that you know it, the next step, what we are supposed to do is we'll import our Chatolama, which is our local LLM that we need to run. And here you have a tool 1. So as I said, whenever it comes to agentic application, if you have your own custom tool, you need to define it. So what is the custom tool that we have? It is the knowledge base. And the task of the knowledge base is to retrieve the relevant documents for the given user query. So def retrieve docs, you have the user query. And here what we are trying to do is you have the retriever. And from retriever, you just have to do invoke and pass your query. So where this retriever come from? We have defined it here. So if you see retriever dot db dot as retriever, and what is the search? Search type is MMR. MMR is nothing but maximum marginal relevance. And how many chunks I need? I need only 3, right? So this is what we are defining here. And in order to run it, you just have to use invoke. And then once you run invoke, if you notice, there are 2 things. One is you have page content, and one more you have metadata. So what I need is, for this particular application, I don't need any metadata. I just need the page content. And once I have the page content for all the list, I will concatenate it. So this is what I'm trying to do. So for every single page content, I will concatenate that in a single list and then convert it into a string. Because at the end of the day, I need the context to be in string. So now if I run this, and if I ask any user query, so this is how your context looks like. So this context needs to be given to the LLM. And what is the first tool? The first tool is the get relevant documents. Now is the second tool. So in order to perform the second tool, there are 2 delimiters if you see. So the first delimiter is tool code, and the second delimiter is tool output. So whatever prompt we are using here, it is from the article that I showed. So if you check my slides, you have this article called Google Gemma 3 function calling example. So inside that they are defined. If you want to define a function calling with Gemma 3, you need to have these 3 delimiters. One is tool code. So let's suppose you have 5 tools. Define all those 5 tools here. So tools is nothing but function, right? So this is very important to understand. Tools is nothing but Python functions that has logic, that has the logic. So now once you have this prompt, if you see you have tool code, this tool code should decide what tool are you supposed to pick. And tool output is nothing but if there is any additional reasoning that it is supposed to do, it is using things step by step, which is nothing but your chain of thought prompting. So chain of thought prompting is nothing but you need to think step by step. And once this is done, you're using your LLM model. And this LLM model, if you want to invoke, you have to use llm.invoke. You have prompt. So this one is doing your tool calling. So this is your first LLM call. First LLM call will decide what tool to pick and what are the arguments that needs to be passed inside that function. So if you see the output, you have tool code, and this tool code has print retrieve docs. Inside this retrieve docs, you have query, and inside this query you have tips to implement features. So this will be passed inside your extract tool call. So once you pass inside extract tool call, it will run that particular function and generate the response. So I hope this was clear. You're asking a prompt, you're checking with LLM what tool to pick, and it will give you this particular line. So once you get this line, you're running it in an interpreter. So interpreter will run retrieve docs function. It will get the context. So this is what we did so far. We are getting the context. So we used one LLM call. If you check this diagram, you're asking a prompt. So once you ask the prompt, you're deciding what are the function definition. You're using the LLM. Now you have the context. Once you have the context, you again have to use LLM for the final answer generation. So if I come back, so now that you have context, if you scroll below, you have a final prompt, answer the user question for the given context. If the context is not sufficient, then you don't have to respond it properly. So you have context, you have user question, and again you are using your second LLM. So second LLM is nothing but LLM.invoke, ask your prompt and generate the final response. So this is where you're generating the response using the LLM from the given knowledge base. And this is the first application where we have developed our agentic RAG. But what is missing? So if you see here, usually you're running every code cell separately. So if you see LLM is separate, your prompt is separate, then whatever response you got from function call is separate, then this is also separate. Now what we'll try to do is we'll use LangGraph, we will define the state, and we will define the nodes. Nodes is nothing but the logic, and logic is nothing but your functions, right? So till here understood, right? So that we can proceed with LangGraph implementation. Any doubts? All right. So we do have 10 more minutes. Right. So coming to the LangGraph implementation, what we are trying to do is whatever about tools you had, there were two tools. One is the retrieve docs and one more is the extract tool call. So you have to define both of these two details. And then we need additional parameters here. One is inside this particular secret, if you notice, you have this line, right? From Google.Colab user data. Inside this, what you're supposed to do is define your Google API key. So if you see, you have Google API key, and how did I get this from? You just have to search for aistudio.google.com. And the reason why I'm using Google API key here is because I want to run GenAI client. From GenAI client, I'm using Gemma 327B IT. Earlier, if you notice, I'm using Chat Olama. So for Chat Olama, I'm using model name. So if I print model name, model name is nothing but Gemma 3N E4B, which is your 4 billion parameter model. So if I scroll down, if I run this again, you have Gemma 3N. So this was the model that was used for Olama, and all these responses that you see was generated from the Olama. But in order to make the things faster for the demo that we have, what I'll try to do is instead of using Gemma 3 from Olama, I'll be using it from Gemini itself directly. So you can replace this. You can directly use Olama as well once you have the GPU support. And now if you see, you're coming to the next line where we are defining our tool call. This tool is nothing but your web search. And once you have web search, we are defining our Google GenAI, where we are using Gemma 3. And then we are defining our LangGraph. LangGraph will define the state from where you have to start and where you are supposed to end. So till here, I hope you understood the import statements. And in order to get Gemma 3 API key, we just have to open Gemini. So in Gemini, okay, I was using VPN, so it's not showing. But basically, what you're supposed to do is, once you open AI Studio, you have to click on Get API. So AI Studio.google.com. On the left bottom side, you will see a button called Get API Key. So you have to click on Get API Key, and then you have to create a new key. So you have to give a name. And once you give a name, your API will start with AI, and then it will have some additional digits. So once you have that, you just have to copy that, come back to Colab, click on secrets, add Google API key, and here you have your value. So if you see, starting to keyword is AI. And now that I've saved, the next thing is you need to create your OPIK tracing part. So if you just click on this, this is your OPIK. Let me open this URL. So once you open OPIK, right, if you notice on your top right corner, you will see these 9 dotted icons. You have to click on experiment management. And here you have new project. You have to define a project name. And here I'm defining local agentic RAG. And once you define this, give any description and make it public. And I've already defined this project, so I will cancel. So if you see local agentic RAG, and I've defined it as DevFest. So this is the project name. And whatever you see on your left hand side at the top, Tarun Arjun, this is your workspace. And here, if you click on my icon and if you see API key, this is the key. So you need 3 details. One is the workspace, which is Tarun Arjun, the project name that you created, and the OPIK API key, which you can get it from the profile. Profile, API key, and copy this. All right. So once you have configured this, you have your LLM. LLM is Gemma 3. And if I do the inference, what is the capital of Germany? The capital of Germany is Berlin. So LLM is working fine. Now coming to the web search, which is our second tool, I'm using DuckDuckGo. Then I'm using browse, which is nothing but invoke, query, and return the context. So if I run a simple prompt, which is black hole, it will generate the response, which is the context. Now we will define the state, which is the final part of our code. So this state will track our query. It will track the context. It will track the tool response because I want to know what was the tool generating. And then the final response, this is the answer generation. So the code is same. So if you look at the code, generate tool call, you have the user query, same prompt. The only change is you have 2 tools now. So the first tool is retrieve docs, second tool is web search. So if your user question is from the document, use retrieve docs. If it is not from the documents, use web search, which is nothing but your web browser. So LLM will decide which tool to pick based on this given prompt. So this is what I was telling. If you want to use function calling with router agent, we will define prompt with delimiters. So this delimiters is nothing but tool code, tool output, and tool call. So this is what we have to define. And the code is same. Once you have your prompt, you just have to inference it. That's it. So tool call equals to LLM client dot model dot generate. This is the Gemini, what you call SDK. So define your LLM, add your prompt, and whatever output you're getting, just return the text. So this tool response is nothing but you will have this thing. So whatever you're seeing here, right, this is your tool response. So this tool response is your first node, and second node is to get this context and give it to your LLM for final answer generation. So if I scroll down, so you have first one to generate tool response, and the second node is to generate your final response. You have the query, now you have the tool response. So you have the tool response, you have tool code. So from inside this, you have to extract the function, run the user query, and extract the output, which is your context. So once you have the context, you have your final prompt, answer the user question from the given context. You have context, you have user question. This is a basic RAG template prompt. But instead of this, you usually have, if the context is not in the knowledge base, say I don't know. So this is how RAG prompt looks like. But here we are building agentic RAG, which should either use knowledge base if it is from the knowledge base. If not, it has to use Google search. So I don't have to define this. You already have the context, which is extracted from the tool. And once you have this, you have your final answer generation. And when you're returning it, make sure you return both final response and as well as context. That's it. And you have 2 nodes. As I said, node is nothing but logic. Once you have logic, define your state. So we have total 2 nodes. One is to generate tool response. And once you get the context, give it to the final answer generation, to LLM call. So start with tool, then tool goes to answer generation go to end. So this is your graph representation. So if you run this to cell, this is how your graph looks like. Start, tool, then final response, then end. So this is the query. So now if I just run this, result equals to graph.invoke have query. So it will take some time. It took 5 seconds. I have my final response. So if I open the PDF, so this is the PDF. So if you see, I asked something related to feature implementation. It said implement 1 or 2 features per cycle. So this is what it did. And then if you look at the tool response, you have tool code, which was using retrieve docs. Similarly, if you ask a question, who is Messi, right? So who is Messi is not there in my document. So instead of retrieve docs, here it has to use web search. So if I run this, you got the response. Now if I run this, instead of retrieve docs, you have web search. So this is what is called routing with function calling. I hope it made sense. And this is the context. And if you want to use monitoring, you just have to import OPIK. From OPIK, you have to get track, then OPIK context. So here, if you see, you just have to define a decorator in Python. And once you add this track, whatever response you have here, right? So I'm running the same thing. If you see, result equals to graph.invoke query and the user query. This is what I'm defining here, graph.invoke query, user query. And then I'm defining a metadata. So this metadata should also tell me what did tool generate. So that is in the metadata, and you have your final response. So now if I run this, you have your tracing. I'll show you where metadata is added. So we'll take hardly 3 more minutes. So if you see this get response is nothing but my Python function. Inside this, you have input and output. Who is Lionel Messi? You have the output. So this is your final response. So if you see, result final response is your output. Here, if you notice, you have metadata. Now, if I click on metadata, it says you use tool response. Inside tool response, you have tool code, which says web search. So this is what I need to track as well. So how did I track it? Just by providing OPIK context, update current trees, you have metadata, tool response, and you're just adding it. So this is your key and this is your value. So this value is being generated from graph. So I hope till here it was clear. Now what we are trying to do is we are just running a UI. So you have Gradio, you have chatbot response. The code again is same. You just have to define your graph dot invoke. You have query. Whatever message is getting, you have to generate the final response. So if you see, this is the final response. And Gradio has only one single widget that can help you build chatbot, which is chat interface. Define the function, give a title and description. That's it. So now if I click on this, you have the live website that you can use. So this is the chat. So this is the deployed URL, which will be active until I run this particular web page. So if I open this PDF, there is something related to common pitfalls. So I'll just ask that question. What are the common pitfalls to avoid while coding? So you have the response, and if you anything related to who is Virat Kohli. So I'm from India, and we have very wide support of cricket. So he's a famous Indian cricketer, and here it is using web search. So as you can see, Virat Kohli is an Indian international cricketer. So yeah, that's it. We saw 4 steps. The first step is how to use Olama models on Colab. Then we looked at document processing, where we took inspiration from Uber article that says how they build their production grade Agentic RAG application. And then you have Agentic RAG application itself, where we are using LangGraph, where I showcased how you can do routing based on the function calling, which is not natively supported in Gemma, but you can do it via prompt engineering with delimiters. And at the end, we had Gradio with just one single widget. We had this particular UI. Cool. So much. It was a very long session.